We are in Unit 7, and this is Note 6, which I decided to add to our unit mostly for my virtual kids, so that when you're at home you can see me going through a few of these problems like I would in class. But we're not learning anything new. This is not new notes, no new concepts. This is just, we're going to be going over some more AP problems. You've already had some in all of your worksheets up until this point, but we're going to be going over some specific AP problems that I was able to find from past AP exams. Okay, so I'm going to start off, and we're just going to do about 3 of these. I'm going to do 3 of these with you, and then the other 4 will be for your assignment. So I'm starting off with number 1, and I put number 1 on here just to remind us that this whole unit we have been using our calculator to evaluate integrals, and we don't necessarily have to be given a calculator to evaluate a lot of these integrals. So this number 1 is a no calculator problem, and it was when it was presented on the AP exam. I don't know what year that was, but whatever year that was, they decided to put it in the no calculator section. Okay? So it's a little reminder that, hey, we can totally do this without a calculator. We have been using our calculators just for convenience, but it's not a necessity in many instances. All right. So in number 1 here, it says, let R be the region bounded by the x-axis. The graph of y is equal to the square root of x. We kind of know what, you should know what that looks like. And the line x equals 4, you should know what that looks like. So I'm going to begin by drawing a little sketch of this graph. We have the x-axis, a square root, which is in the first quadrant, and the line x equals 4, which is a vertical line of x equals 4. So all of our action is happening in the first quadrant in this problem. Don't assume that it will always be that way, but in this problem it is. So we've got, there's just my axis, and the x-axis is one of our boundaries. Y equals square root of x, and the line x equals 4. When x is 4, y is 2, right? So that's going to be one of our points of interest on there. So here's a boundary, here's a boundary, and the square root curve looks something like that. So our region R, they're calling it, is right here. There's our region. All right. In part A, we want to just find the area of that region. The area of that region. Well, I know this is a really basic integral. So the area is always the top curve minus the bottom curve. So our area will equal the integral from 0 to 4. Those are our x boundaries. And top minus bottom is square root of x minus 0. So this is just square root of x dx. Okay, we don't have a calculator. We can totally do this by hand. So let's remind ourselves how to do that. We think of square root of x as x to the 1/2, and we apply the power rule for integrals. So x to the 3/2 times 2/3, and we are evaluating that from 0 to 4. When we put 4, I'm going to take that 2/3 out. When we put 4 in for x, we'll have the square root of 4, which is 2, and then 2 cubed is 8. Minus, and now we're going to put 0 in for x, and the square root of 0 is 0. So we get that expression. So this would be a safe stop spot. If this had been a multiple choice answer, let's try to focus that a little bit. If it had been a multiple choice answer, we just would have had 16/3 there. Okay. So yeah, note that you can take out that 2/3. It's just a number. You can take it out and then just plug in your numbers, your boundaries to the remaining expression. All right, part B. Find the value of h such that the vertical line x equals h divides region R into 2 regions of equal area. I'm just going to sketch this graph again just so I have something to mark up here. So that's 4, and they're saying that there's some x value between 0 and 4 such that when we that vertical line x equals h, it might be somewhere around there. I'm going to call that h. It divides this region into two regions of equal area. So, and we want to find the value of h. Find h. Not just set up an integral which yields the value of h. No, we have to actually find h here. So, I'm going to use the fact that I just now up here found the area of the entire region. So I know that the area of the entire region is 16/3, right? So that tells me that the integral from 0 to h of the square root of x should be half of 16/3, right? If h is dividing this region into two regions of equal area. So the integral from 0 to h of my square root of x dx should be half of that area, the entire area, which we just now found to be 16/3. And we need to solve this equation for h. So this is an integral equation that we're going to solve. Okay? I'm going to begin by going ahead and doing the antiderivative again, taking the antiderivative. So I'm thinking of that as x to the 1/2. I know we just did this. This is going to be 8/3 over here. So the integral, or the antiderivative of x to the 1/2 is x to the 3/2 times 2/3. And we are taking that from 0 to h. And that whole thing is 8/3. Notice how I keep my equation all the way through. This is an AP question. They have got to be able to follow your work. It has to be logical. There can be no errors. Don't start working on one side and then at the end throw the 8/3 back in. Keep it there, okay? All right, so this will be 2/3 times, if we put h in for x, we get h to the 3/2 minus 0 in for x is just 0, and that's 8/3. So we have this equation to solve now. If I multiply both sides by 3, the 3's are gone. I'm going to take half of both sides, and then I'll have h to the 3/2 is equal to 4. And now we have to finish solving for h. I'm going to raise both sides to the 2/3 power. And we get h is equal to 4 to the 2/3, and I'm stopping there. Okay? Plus I can't take a cube root of 4, so I'm definitely going to stop there. Okay? Alright, so we found that value of h. Alright, part C, find the volume when the solid find the volume of the solid generated when r is revolved around the x-axis. So another sketch here. We're going to now take this same region, and here's my region, and we're revolving it around the x-axis. So revolving it around the x-axis. So it's going to be kind of a bullet-shaped figure, solid, right? Okay. So we know how to do that. We know how to find the volume. Actually find the volume, not just set up an equation. We actually have to find the volume. All right, so I'm going to draw a dotted line on my axis of revolution, the x-axis. Okay, and then from my axis of revolution to the far side of my region, that's going to be my capital R. And from the axis of revolution to the close side of my region would be my lowercase r, but there is no such region because this region lies right on the axis of revolution. So capital R is just the square root of x minus 0, so just square root of x. So my volume is always the integral of my area, right? The area, integral of the area gives volume. So the area here would be pi r squared, right? dx, and it's a dx, so we're going from 0 to 4. So I'm going to put in what I have there. pi times, I need r squared. Well, the square root of x squared will be x. And now I can actually find this antiderivative. So the antiderivative here will be pi over 2 x squared, and we are taking that from 0 to 4. Okay? So again, that pi over 2 can come out. Put 4 in for x, minus 0 in for x, and this turns out to be 8 pi. Or we could have stopped right here. Okay? All right, part D. The vertical line x equals k divides region R into two regions such that when those two regions are revolved around the x-axis, they generate solids with equal volumes. Find the value of k. So we're doing something similar to what we did in part B, except now we're dealing with the volume rather than the area of R. So I'm going to take this solid that we just found the volume of, and they're saying that there's some value of x equals k, and it'll be between 0 and 4, such that when we revolve that around, it splits this volume into two volumes of equal magnitude. Okay? So two equal volumes. So again, I know the entire volume is 8 pi, so I'm just going to go from 0 to k. That should be half of 8 pi, right? So the volume from 0 to k of pi r squared should be half of the entire volume, 8 pi. So again, r squared is x. When we take the antiderivative here, we get pi over 2x squared from 0 to k is equal to 4 pi. I'm going to take out my pi over 2, put k in for x, minus put 0 in for x. And that should be 4 pi. Okay, so I'm going to multiply both sides by 2 over pi. Multiply on both sides by 2 over pi. So I get k squared is equal to, the pi's cancel and we just have 8. So k is the square root of 8. And that's it. So yeah, on this problem, we can definitely do some simple integration, right? And you know, the whole point, the whole reason that I let you use a calculator so much is just so that we could do a lot more problems, and the setup is a challenge with some of these. But in this one, we had a simple integral. It didn't take long to take the antiderivative and find out these answers. Okay? All right. Next up, I'd like to take a look at number 2 with you. And number 2, the rest of the problems are all with a calculator. So, okay, got my calculator. Alrighty, so let's see. In number 2, it says let R be the region enclosed by the graphs of y equals e to the x and y equals x minus 1 squared, and the line x equals 1. That's a vertical line, x equals 1. So let's see what we're talking about here. I'm going to go to my y equals e to the x and x minus 1 squared. I can't graph x equals 1, I just have to know where that is, right? So I don't just focus on the first in the first quadrant. Let's see what's going on. I'm going to do zoom forward just to get a kind of a general graph, see what's going on. Okay, so this is what I see, and I need to look at where are we at. So I also want to have the line x equals 1. Well, x equals 1 is going to be right here, right? So where is the region bounded by these three things? It looks to me like it's right there in the first quadrant, like that. So I'm going to sketch this here just so I have something to kind of mark up a little bit. So it does look like it's in the first quadrant again this time, but I always, never assume that it's always going to be in the first quadrant. So I'm sketching this. So right here, that looks like it's 1. Is that 1? If I do a little math, is that 1? Yeah. When x is 0, we're at 1 there. When x is 0, we're at 1 here. So yeah, they do intersect at 1. So that value is 1. And then we're over here when x is 1. I'm going to make it kind of not to scale so that I can see what I'm doing here. So this is going to go up like this. And then this is going to go down like that. And then I'm going to have that vertical line here. So there's my region. Okay. This is my e to the x graph. This is my x minus 1 squared graph. And this is my x equals 1. Okay. All right. First off, we want to find the value of r. Find the value of that region. So that's not too bad because all we have to do is use top minus bottom, right? Let me get to another color here. Top minus bottom. So the area of r is going to be the integral from 0 to 1. Those are my x boundaries. 0 to 1. And then top minus bottom, e to the x minus x minus 1 squared. That's top minus bottom, dx. So I definitely need to show what I'm finding, and then we're going to use our calculator to find that. It says to find, not just write the integral, find. So I have to go ahead and use my calculator to get that. So I'm going to go to my home screen, and I need math 9, 0 to 1. E to the x is stored in for my y1. The x minus 1 squared is stored in for my y2. dx. And I get a 1.385 if I round that to 3 decimal places. Remember that we can also just truncate. So either one of those answers would be acceptable to AP. All right, find the volume of the solid when r is revolved around the x-axis. All right, let's see if I can just do this over here without redrawing it. So here's my axis of revolution going around the x-axis. So I'm going to, let me get a different color here. My big R will be from my axis of revolution to the far side of my region. That's my big R. Little r is from the axis of revolution to the close side of the region. That's my little r. Yeah? So big R, my big radius, is going to be the e to the x minus 0. The x-axis is y equals 0. Little r is the x minus 1 squared minus 0. And then my volume will be the integral, again from 0 to 1, because we're going from x equals 0 to x equals 1. And it'll be pi big R squared minus pi little r squared. We get, remember the area, area minus area, because we don't want this blank area, right? dx. Okay? So, since I named big R and little r, I don't have to rewrite this using the e to the x and the x minus 1 squared. However, it's going to be tricky for you to be careful if you don't rewrite it, because you might get a little confused. So I'm going to say pi times big R squared is e to the x squared, right? Minus pi little r squared is x minus 1 squared squared. Well, squared will be x to the 4th. And remember, when this here we would multiply, so that would be 2x, e to the 2x there. So when I type that in, I'm going to be using e to the 2x there. So math 9, 0 to 1, pi times e to the 2x minus pi times x minus 1 to the 4th. Okay? So we get 9.408 if we round, or 9.407 if we truncate. So either one is correct. All right, set up but do not integrate. Set up but do not integrate. An integral expression in terms of a single variable for the volume of the solid generated when R is revolved around the y-axis. Now we're going to take this and revolve it around the y-axis. Since I've marked this up pretty good, I'm just going to come over here and resketch it. So my shape looks something like this. And now I want to revolve this around the y-axis. Well, we have a choice. We can use the cylindrical shell method, or we can use the disk and washer method. If we use the disk and washer method, we're going to need two different integrals separated at y equals 1. So because I don't want to use two separate integrals, I'm going to use the cylindrical shell method. So to do that, we draw a vertical slice, and we draw our little representative cylinder, right? And now I can see R. R is just going to equal x, because that's how we defined x, right? Or that's how we just defined R. So the radius of the cylinder is just going to be x. The height of the cylinder is top minus bottom, e to the x minus 1 squared. Okay, and now my volume is just the integral 0 to 1 of 2 pi r h dx. Okay? So again, since I named what r was and I named what h is, I can just leave it like that. And I think I will here. Okay? And that is that problem. Now, our equation would look quite different if we did disk and washer method. It would look quite different. In fact, it would be this. The volume would be 0 to 1. We would have to solve everything for x, and so we would have dy's everywhere, right? So it would be pi times 1 squared minus pi times square root 1 plus, square root y plus 1 squared dy. That would be one piece. That would be the piece from 0 to 1. And then we would need to add the piece from 1 to e. This top, that happens when y is e up here. And that would be pi times 1 squared minus pi times natural log y squared dy. So very, very different looking integrals that would yield the same thing. All right? But the cylindrical shell method for these vertical axes of revolution is very convenient. Very convenient. Okay, I needed to look through this and see which one I wanted to do with you, and I've picked number 4. I like number 4 here. It has some different things going on with it. All right, so here in this AP problem, they gave the graph, they gave the picture. And remember what I said earlier, even though they give you a picture, you are still going to have to put this into your calculator, and because you're going to need to find some information about this, okay? Namely, we need to find that point, and that point, and that point. Okay? So, but they describe R and S, and they're all in the first quadrant, it says, and R is bounded by this curve and this curve, so that's R, and then S is bounded by, oh, the y-axis. I was like, wait a second, those are the same two curves. R is bounded by the x-axis and those two curves. S is bounded by the y-axis and those two curves. All right, I thought maybe I had a typo there. Okay, so I am going to put these into my calculator. Let me get rid of all this stuff. All right, so I have 2 minus x cubed and tangent x. Doesn't look too bad. I'm going to zoom 4 first. And all I want is this region right there. Oops, there's a lot of glare there. All I want is this little region right here. So I'm seeing way too much, way too much. So I think I'm going to go, it looks like one, maybe I'll just go to like 1.5, maybe, not even, maybe 1, yeah, 1.5 should work. And then up here, I think I'm going to go to like 2.5. So on my x min, I'm going to go to 1.5. So I think I'm going to start at negative 0.25, just to see a little bit on the left. And then for my y's, I'm going to, again, go from like negative 0.25 to, what did I say, 2.5? I think that should do it. Okay, I like that a little bit better. Even though it doesn't look a lot like this, I could make it look more like it, but I see it. That's definitely that shape, okay? So, all right. Find the area of R. We want to find the area of R. So, here's R. We want to find the area of this guy. Well, we have a choice, okay? If we do a dx here, so that would be going from 0 to whatever x value that is. Let's go find that x value. Second calc, I don't have, let me put in 0 here real quick. So second calc intersect, and then I do want that one. I don't want that one, I want that one. There it is. It's 1.259921, right? So I'm going to let, first I need to say what I did. So, oh, that's 2 minus x squared. 2 minus x squared, 2 minus x, oh, I have the wrong equation in here. I just saw that this is a cubed, not a squared. Did I do that? Oh, I did do it right. Okay, good, good. I was like, wow. Okay, so of course it did look like a cubic curve. Okay, this is 0 at x equals, and now what was that? Did I lose it? No, I think I lost it. Okay, why isn't it going? Hang on. Let's do second calc intersect, enter, enter, enter. Okay, that got me that. Well, that did get me that intersection, which I will need. I will need that. Since I got it, let me go ahead and write that one. So I'm saying that these two intersect at x equals 0.902155, and I am going to store that in for A, and y is equal to 1.2657 dot dot dot, and I'm going to store that. I'm actually, since it's a C, I'm going to store that in for, since it's a Y, I'm going to store that in for C. So let's go do that before I do anything else. So quit. I'm going to take my X coordinate and I'm storing it in for A, and I'm taking my Y coordinate and storing it in for C. Okay. Now I still want to get this 0 right here. So what is that? intersect. Yes, I want that curve. No, I don't want that curve. I want that one. There it is. Okay, so this is 1.2599 ... And I'm going to store that in for, I don't know, I'm going to store that in for b, I guess. So I'm going to take that x value, and store it in for b. So now I have all of my numbers in there, so I'm kind of good to go here. All right, so for the area of R, again, still looking at this area of R, I can either do top minus bottom or right minus left. If I do top minus bottom, I'm going to need two integrals. And that's okay, it's not a big deal, but I will need two integrals. Okay. If I do right minus left, I'll only need one integral because it's always this curve minus this curve. But if I do right minus left, I need to go and solve these for x. So either one is fine. You just pick which is the lesser of two evils for you. Okay. I think this time I am going to just do two integrals. So I'm going to do the area. I'm going to say the area of R is, okay, first I'm going to go to this point, and I called that x equals a, right? I'm going to go from 0 to a first. Top minus bottom is my tangent x minus 0. And then I'm going to add to that the integral from a to this x value, which is my b, right? So from a to b of that top minus bottom, which is 2 minus x cubed minus 0 dx. So when I put that into my calculator, I'm going to have math 9, okay, math 9, 0 to a, and then tangent x, I do have it stored in for y2 if you want to use that, or you can just type in y2, I'm sorry, tangent x dx plus math 9, a to b, of my y1. Okay, and I see this and I know I made a mistake somewhere because I know that that's not the right answer. Oh wait, no, that's not the right answer. Okay. Oh, you know what? Yes, it is. It is the right answer. Sorry. I was looking at the wrong problem. Okay, so yeah, that is correct. So 0.729. I thought maybe I had typed it in wrong or something. Okay. So yeah, I can see I'm looking at my my solutions that I made that I posted, and when I did this the other time, I did do right minus left. So that got me the same answer. Okay, next up, find the area of S. Area of S. Well, for the area of S, I'm definitely going to do top minus bottom because the 2 minus x cubed is always on top and the tangent x is always on the bottom. So that's not going to be nearly as bad. Area of S will be the integral from 0 to a of top minus bottom, 2 minus x cubed minus tangent x dx. So math 9, 0 to a, y1 minus y2 dx. And I get 1.161 or 0. So remember, AP allows us to either round or truncate. Okay. All right. Next up, find the volume of the solid generated when S is revolved around the x-axis. So we're taking S here, we're taking S and we're revolving it around the x-axis. Okay? So from the axis of revolution to the far side of your region is your big R, big radius. So that will be 2 minus x cubed minus 0. From your axis of revolution to the close side of your region is your little r. So that will be the tangent x curve minus 0. So the volume will be the integral from 0 to a of pi times your big R squared minus pi times your little r squared. Back to our calculator. Math 9, 0 to a, pi times our big R, I should have put in y1 there, squared minus pi times our little r, oops, I will get this. My fingers are not wanting to do this right. I should have just done the y2. Anyway, and then dx. And we get 8.331 or 8.332 if we round. So I like to round, so my answer would be 8.332, but AP would also accept 8.331. Okay? All right, so that leaves 4 of these for you to do, and it'll be a nice practice before our test.